AP and BP stars are peculiar stars of types A and B which show overabundances of some metals, such as strontium, chromium and europium. In addition, larger overabundances are often seen in praseodymium and neodymium. These stars have a much slower rotation than normal for A and B-type stars, although some exhibit rotation velocities up to about 100 km per second. Magnetic fields. They also have stronger magnetic fields than classical A or B-type stars in the case of HD 215,441, reaching 33.5 kg. Typically the magnetic field of these stars lies in the range of a few kilogram to tens of kilogram. In most cases a field which is modeled as a simple dipole is a good approximation and provides an explanation as to why there is an apparent periodic variation in the magnetic field. As if such a field is not aligned with the rotation axis, the field's strength will change as the star rotates. In support of this theory, it has been noted that the variations in magnetic field are inversely correlated with the rotation velocity. This model of a dipolar field, in which the magnetic axis is offset to the rotation axis, is known as the oblique rotator model. The origin of such high magnetic fields in AB stars is problematic, and two theories have been proposed in order to explain them. The first is the fossil field hypothesis, in which the field is a relic of the initial field in the interstellar medium. There is sufficient magnetic field in the ISM to create such high magnetic fields, indeed, so much so that the theory of ambipolar diffusion has to be invoked to reduce the field in normal stars. This theory does require the field to remain stable over a long period of time, and it is unclear whether such an obliquely rotating field could do so. Another problem with this theory is to explain why only a small proportion of A-type stars exhibit these high field strengths. The other generation theory is dynamo action within rotating cores of AB stars. However, the oblique nature of the field cannot be produced, as yet, by this model, as invariably one ends up with a field either aligned with the rotation axis, or at 90 degrees to it. It is also unclear whether it is possible to generate such large dipole fields using this explanation, due to the slow rotation of the star. While this could be explained by invoking a fast rotating core with a high rotation gradient to the surface, it is unlikely that an ordered axisymmetric field would result. Abundant spots. The spatial locations of the chemical overabundances have been shown to be connected with the geometry of the magnetic field. Some of these stars have shown radial velocity variations arising from pulsations of a few minutes. For studying these stars, high-resolution spectroscopy is used, together with Doppler imaging, which uses the rotation to deduce a map of the stellar surface. These patches of overabundances are often referred to as abundant spots. Rapidly oscillating AB stars. A subset of this class of stars, called rapidly oscillating AB stars, exhibit short timescale, millimagnitude photometric variations and variations in radial velocities of spectral lines. These were first observed in the highly peculiar AB star HD 101065. These stars lie at the bottom of the delta Scuti instability strip on the main sequence. There are currently 35 known ROAP stars. The pulsation periods of these oscillators lie between 5 and 21 minutes. The stars pulsate in high overtone, non-radial pressure modes.